I'm going to talk about the trapezoidal approximation method. I'll assume you're familiar with the left and right side rectangle approximation methods. I'll also assume you're familiar with the midpoint rectangle approximation method. If you're not familiar with any of those methods, I would encourage you to watch my videos on those topics. All right, let me draw a picture and then we'll continue. All right, suppose this blue curve corresponded to the graph of f of x, and suppose we wanted to approximate the area below the blue curve above the x-axis with respect to the x values between 2 and 8. So in other words, suppose we wanted to approximate the following integral. Okay, now we could use any of our rectangle-based methods, and I think you would agree that the rectangles don't always cover the area as well as you might like, especially when you have just a few rectangles, right? The flat roofs just aren't a good approximation for a lot of regions. Okay, watch me cover this region with 3 shapes of equal width that can approximate the region much better. What if instead of using rectangles, we had shapes that had slanted roofs, so to speak? All right, so can you see how these rectangles with the parts of the tops chopped off actually make a better approximation? Okay, so these shapes are referred to as trapezoids, okay, and we can use trapezoids to get better approximations to integrals. Now, you might be thinking, well, great, why doesn't everybody use trapezoids? Well, first of all, finding the area of a trapezoid is going to involve more work than finding the area of a rectangle, okay? So yes, it'll give you a better approximation, but you'll have to do some more calculation to get that improved accuracy, okay? So that's why people don't always use the trapezoidal approximation method. Now, to find the area of a trapezoid, maybe you've memorized the formula. Okay, if you haven't, you can still always derive it in a minute or two by noticing that trapezoids are always equal to a rectangle plus 1 or 2 right triangles. Okay, and if you know how to find the area of a rectangle and 2 right triangles, then you're good to go. Okay. So, in fact, you could try to find the area of the leftmost trapezoid in my picture, and you would see that that's equal to the width of the trapezoid multiplied by the following fraction. Now, let me make a comment about that fraction. Notice that fraction is equivalent to the average of the function values with respect to the left and right sides of the trapezoid. Okay? So it just turns out that the area of the trapezoid gives an expression that can be interpreted that way. Okay? So I can to that area of that one piece, I can add the area of the other two trapezoids. Okay, and now we can simplify that expression, and we would get f of 2 plus 2f of 4 plus 2f of 6 plus f of 8. All right, now go ahead and work it out yourself and convince yourself that this approximation is equal to that expression. All right, now what if we had used the right side rectangle approximation method? What would we have gotten for the corresponding expression then? Well, then we would have had 3 rectangles, all with a width of 2. And the heights of our rectangles would have been, for the right side rectangle approximation method, the heights would have been f of 4, f of 6, and f of 8. Now, suppose that we found the expression with respect to the left side rectangle approximation method. Well, then all the widths, let's assume, are 2, and the heights of our rectangles would be f of 2, f of 4, and f of 6. Okay? Now, what would happen if we added the 2 purple expressions together and divided by 2? So you can work that out yourself, and you will see that you will get this expression. Okay, now notice we got the same expression as we did for the approximation that used the trapezoids. Okay, so this brings us to an interesting result. What's referred to as the trapezoidal approximation method is equivalent to finding the average of the results from the left and right side rectangle approximation methods. Okay, let me spell that out so that that's clear for everybody what is going on here, what we just noticed. Okay, the trapezoidal approximation method is equivalent to finding the average of the left side rectangle approximation method and the right side rectangle approximation method. Okay? Let me say it another way. So if you found the left side rectangle approximation method value for n rectangles, that's sometimes denoted by L sub n. And if you found the right side rectangle approximation method for n rectangles, that's sometimes denoted by R sub n. Okay, and the average of those two values would be the sum divided by 2. That's equal to the value with respect to the trapezoidal approximation method for n trapezoids. That's often denoted by T sub n. Okay? So that is probably the nicest way that I know to present the trapezoidal approximation method so that it's easy for you to remember it. Okay? Now, let's do an example together. All right? Let's find an approximation to this integral using 3 trapezoids all with the same width. Okay? So if you like, I'll make a picture to show you what's going on. The graph of x squared plus 1 is a parabola. And we are interested in the region with respect to x values between 0 and 3. Okay, so that picture represents the region we're going to find, that we're going to work with. We're going to find an approximation to the area of that region. Okay, and so the 3 trapezoids will look like the following. Okay, and so I'm going to take advantage of the fact that the sum of the areas for the 3 trapezoids corresponds to the average of what I would get by using the left and right side rectangle approximation methods. So finding the left side rectangle approximation method with 3 rectangles would give, so all the rectangles have a width of 1, so 1 times the sum of the heights of the left side, so f of 0 plus f of 1 plus f of 2, and that gives 1 plus 2 plus 5, or 8. All right. Now, using the right side rectangle approximation method, I would get 1 times the sum of the function values with respect to the right side, so f of 1 plus f of 2 plus f of 3. That's equal to 2 plus 5 plus 10, which is equal to 17. And so the trapezoidal approximation would be the average of those 2 values. So 8 plus 17 divided by 2 would give 25 halves. All right? Now, I would like you to try an example. And you will most likely need a calculator for this one. I'd like you to approximate this integral by using 5 trapezoids of equal width. All right? So pause the video and work on that and get a value for that. Okay, so let me, just in case, just to make it absolutely clear, so I want you to use the trapezoidal method with 5 trapezoids of equal width. Okay, so do that now, please. All right, so I'll go ahead and do that as well. So each trapezoid, rectangle, they're all going to have a width of 1/5. Okay. If I first found the left side rectangle approximation method with respect to 5 rectangles, each rectangle would have a width of 1/5, and I would sum the heights. So I would sum f of 0, f of 1/5, f of 2/5, f of 3/5, and f of 4/5, where I'm defining f of x to equal the square root of x squared plus 1. Okay, now you can take all the corresponding square roots with the calculator, find the sum and multiply by 1/5, and I got 1.109. Okay, and then finding the corresponding right side rectangle approximation method value, I would have to find 1/5 times the sum of the function values f of 1/5 plus f of 2/5 plus f of 3/5 plus f of 4/5 plus f of 1. And working that out on your calculator, you will get 1.191. Okay? Now, adding those two decimals together and dividing by 2, you will get the trapezoidal approximation method, which is, for this problem, 1.15.